So in the beginning of chapter 5, we are going to start talking about this idea of area. You know, we have found areas of many things throughout the years, right? You know how to find like area of a circle, area of a rectangle, area of a triangle. Well, if you have an area of a curve, that's a little bit different. So if I have a particular function and I want to find the area underneath that function, we have to have a way of doing this. Now, if it's a nice shape, like a rectangle or something, we can find it. Even more awkward shapes, if we can break them into triangles and rectangles, you know, it's easy to find the area of it. But if I just have a curve like x squared, and I wanted to find the area between the x-axis and x squared on the interval 0 to 1, I can't really just break this into nice shapes. So what we could do is break this piece into rectangles and get the area by adding up areas of all these rectangles. But will that be exactly the same as my curve? No. If I'm using these rectangles, can you tell me, would the area I get be bigger or smaller than the true area? Bigger, because those rectangles are going above the curve. We call that an overestimate. Okay, we could get more accurate by making those rectangles smaller, right? The more rectangles I do, the more and more accurate it's going to be. All right, and so this is the idea of what's called an over and under estimate. That's what we're going to work on today, using rectangles to estimate area under a curve. So, if I want an under and over estimate of the area of the region f of x equals x squared on the intervals 0 to 3, and I'm going to do it 2 times. One time I'm going to use 5 rectangles, and one time I'm going to use 10 rectangles. All right. So you can certainly draw a picture, and I probably will for this first one, just to kind of help us get started. So we know like 0 squared is 0. 1 squared is 1. Make this graph smaller. Okay. So we could plot x squared. That's just this parabola. And so I'm trying to estimate the area between that and the x-axis. All right, if I am breaking it into 5 rectangles, so the length of this interval from 0 to 3 is 3, right? Dividing it into 5 rectangles. So the width of each one would be 3/5, or 0.6. So if I were going to use these to estimate my height, we are not going to draw a picture on every one, but for the first example, I'm using a picture to kind of illustrate what's happening. All right, if I wanted an over estimate, that means I'm looking at the rectangles that are above my curve. Okay, so it would be like these red rectangles here. How do you find the area of a rectangle? Length times width. Okay, so this is my overestimate. I'm going to put a little subscript 5, so I know it's with 5 rectangles. All right, can we agree all of these rectangles have the same width? 3/5? So could I just put that out in front? And then I'm going to have the 5 heights of those rectangles in there. So the first one, the x I'm plugging in is 3/5. How do we get the height then, the y value? We know the curve is x squared, right? So it would be 3/5 squared. Can I write that as a decimal? Does that bother anybody? So 3/5 is 0.6 squared. That way I just can use some fewer parentheses. Okay, the next one is at 6/5, so that's 1.2 squared. The next one, I'm just adding my change in x. Okay, we're going up by 3/5 or 0.6 every time. So what's the next x value we would plug in? The next one? And the last one? And those are squared because my equation was x squared, right? We're measuring the y value of that curve at those points. So everybody grab a calculator, not something I say to you often in here. And plug in, what do we get for our overestimate? Okay. All right, we know that's not the true area. It's a little too high, but that gets us a ballpark. If we want to get more accurate, we could look at the underestimate with 5 rectangles. What the underestimate would do is draw these rectangles below the curve. So instead of using the 3/5 or the right-hand point, we would have to start at the left hand. So the first one would look like this. The second one would look like that. Third one. Fourth one. And the fifth one. So we can see those rectangles are all below. All right. So my width is still 3/5. And we still have to add up the 5 rectangles. For the first rectangle, I didn't start at 3/5. What did I start at? 0. So to plug it in, we just get 0 squared. Then the next one I put in 3/5. We're going up by 3/5 each time, so it would be 0.6 squared. The next one would be, the next one would be, and the last one. And what do we get for our estimate? All right. So look at what we did here. They both had the same number in front. They both had 3/5 in front. They both had these, the 0.6, the 1.2, 1.8, 2.4. The only difference was the first and the last point. Okay, this one started at, the underestimate started at 0, the overestimate started at 3/5 and ended at 3. Sometimes these are also called left and right hand sums. So the left hand sum was what turned out to be our underestimate here. We have the interval 0 to 3/5, we started with the left hand point. And so that means we ended before 3. The right hand sum would be starting at 3/5 and using the right hand sum. So you go all the way to 3. If I called them left and right, how would you know at the end which one was an over and which one was an under? It depends on if your function's increasing or decreasing, actually. Yeah, whichever one's bigger.
Sure.
So you could look at a graph. If it's increasing, your overestimate would be the right-hand sum. But if it were decreasing, they flip. But we could just look at the bigger and smaller numbers as well. Okay, now let's do the same thing with 10. So if I want my overestimate with 10, what's the width going to be this time? 3/10. And I will have 10 things in here. Because I'm adding up the area of 10 rectangles. Okay, so without drawing it out, let's just think about it. The overestimate, we've already said for this one, would start with the right-hand sum. So the first piece, that first rectangle, would be starting at 0 and ending at 3/10, or 0.3. So if I'm using the overestimate here, the first number I'd plug in would be 0.3. And I know I'm going to square it because I'm plugging it into the equation, which was x squared. Once you have the first point, you can get all the others. We're just adding our 3/10 each time. So if I add 0.3, I get 0.6 squared, 0.9 squared, 1.2 squared, 1.5 squared, 1.8 squared, 2.1 squared, 2.4 squared, 2.7 squared, and 3 squared. What do you get?
2.
So for my underestimate with 10 rectangles, still with the 3/10, still going to have 10 things here. But instead of starting at 0.3, what would be the first number I plug in? 0. And then we just add our 0.3 each time. So 0.3 squared, 6 squared, 0.9 squared, 1.2 squared. And so you'll notice this one ends before 3. It ends at 2.7. If you want to make life easier, you could bring up what you just typed in. The only difference is instead of having a 3 squared, we had the 0 squared, right? So you could bring that back up and just change that point. And so what do we get? So have I figured out the true area under this curve? No. Have I gotten close? Which one's more accurate, with 5 or with 10? With 10. And we would assume then the real answer is somewhere between the over and underestimate. If I asked you to estimate the overall, what do you think you could do with those numbers? Yep, find the average, add them up and divide by 2. Again, not probably going to be the exact answer, but it would get us pretty close. All right, any questions on what we've done there? Let's try another one. All right, so if we don't want to draw a picture every time, we can kind of figure this out. A lot of times what I'm going to ask you is find the change in x. How much is x increasing or decreasing each time? And so if we look, it's starting at 1 and ending at 3. So what's the length of that interval? 2. And I want to divide it into how many pieces? So my x is going to be changing by 1/4, or if you prefer decimals, 0.25 each time. All right, so let's try this without knowing which one is an over and underestimate. We'll label that in a minute. Okay, the width of all these rectangles in is the 0.25. So I'm adding together 8 things. We are starting at 1. One of these will start at our starting point. So let's start there. If I do 1 for my first point, where am I plugging the 1 in? To the function, to get the height of the rectangle, which is 9 minus x squared. So I have 9 minus 1 squared for the first one. All right, what will be the next x value I plug in? I'm going up by 4, so 1.25. So 9 minus 1.25 squared. And I'm going to keep adding 0.25. So the next one will be 9 minus 1.5 squared. 9 minus 1.75 squared. 9 minus 2 squared. 9 minus 2.25 squared. 9 minus 2.5 squared. 9 minus 2.75 squared. If you start with the left-hand point, so we started with 1, we should end before we get to 3. All right, let's plug this in. So that's 10.3125. I don't know yet if this is an over or an underestimate. We could call it a left-hand sum. I got it by doing the left-hand endpoint. When I do the second one, we're still multiplying by 2.25. We're still adding 8 things. What would be the first number I plug in? Think about the first rectangle goes between 1 and 1.25. So we either start at 1 or we start at the 1.25. So this time we'll do that. And we just keep adding 0.25. And you'll notice all of these points are the same. We had them all. But I don't have the first point. And where does this one end? So it's just a difference in the first and the last point. I change that. You get 8.3125. So which one was an overestimate? And this would be my underestimate. And the real number is somewhere in between them. Okay. How are we doing so far? You guys following what we're doing? Let's look at one one more. My change in x, the length of this interval. So it starts at 0 and ends at 3. So you're basically subtract those two and divide by the number of rectangles we want. So we get 3/6 or 0.5. So for all of these, the rectangles will have a width of 0.5. We have 6 rectangles we're adding up. So if you think about it, starting at 0, the next one, if we add 0.5, will be at 0.5. So for my first one, what would be the first x value we plug in? I mean, we can do it either way, right? One of them will plug in 0 first, and one of them will plug in 0.5 first. It doesn't matter. If I wanted my left-hand sum, we would start with our left-hand point. So I put in my 0, and I'm putting that in for x. 13 minus 3 times 0. 13 minus 3 times 0.5. 13 minus 3 times 1. 13 minus 3 times 1.5. 13 minus 3 times 2. 13 minus 3 times 2.5. I know, 27.75 for that one. So for the next one, the only difference is I'm not going to start at 0. I'm going to start at 0.5. And this one will end at 3. What do you get for that one? Hmm?
40.75.
How about 23.25? Okay, so this is time consuming. It would be great if there were a shorter way, right? And so what we're going to start talking about is something called summations. Okay, it's a shorthand. So we have perhaps seen this formula before. It's a sigma, it's called a summation. when I see this, it says you're going to add up from I equals 1 to n each term. So, for instance, if I said the sum from I equals 1 to 10 of I squared, that means you're doing 1 squared plus 2 squared plus 3 squared plus 4 squared. When do I stop? Mm-hmm. Right, so this is a shorthand rather than writing out every little piece. If I added up all the squares. It actually turns out to be 385. So what we're going to practice now is just writing, taking a summation notation and writing the expanded notation, which is what I did here. Expand it out. What is this telling me? So for this one, if I said the sum from k equals 1 to 7 of k plus 1. So that tells me k is the number that changes each time. The first one I plug in is 1. It always just goes up by integer values. What's the last one I plug in? Now, if you want to go ahead and just add those, you're also welcome to do that. If you wrote 2 plus 3 plus 4, that's fine. So we get 35. So if I said the sum from n equals 1 to 6 of 2 to the n, what would I write down? Plus 2 to the third, plus 2 to the fourth. When do I stop? And we could add all those up. And get 126. All right, the next one. Sum from j equals 1 to 5 of negative 1 to the j plus 1 over j squared. So the first number would be negative 1 to the, can I go ahead and say 1 plus 1 is 2 over 1 squared. Okay, if I plug in a 2 for my j, I get negative 1 to the 2 plus 1 is 3 over 2 squared. Plug in a 3, I get negative 1 to the 4th over 3 squared. If I put in a 4, I get negative 1 to the 5th over 4 squared. And if I put in a 5, I get negative 1 to the 6th over 5 squared. What's that negative 1 to a power doing? Yeah, it's switching the exponents between odd and even, which means when you take negative 1 to that power, it's changing. One term will be positive, the next one's negative, and so forth. All right, so if I add this up, that one gives me a beautiful 3,019 over 3,600. All right, do we kind of understand what the summation notation is telling us? Okay. So I think I'm going to stop here. I really wanted to get through one more slide, but I'm going to do that tomorrow. Your homework, I have a handout for you. Five through 9, we will talk about at the beginning of class tomorrow. So you have to do 1 through 4 and 10 through 12. And then at the beginning of class, we'll do that next slide, and I'll give you a little time to finish those middle ones. Okay?